In real experimental science, the fact that you never know numbers absolutely exactly, but that there's always some kind of uncertainty, is really important, because it governs how precisely you can know whatever it is you're trying to deduce from the numbers you measure, and that can be really important. So at A-level we just introduce this idea of uncertainty a little bit, but if you go on and do experimental science, you'll discover it's something you spend actually quite a lot of time really worrying about and making sure that you know your numbers as precisely as you hope you do before you start drawing conclusions from them. So if, for example, we say, right, I know the mass of this stuff that I've got to the nearest 0.1 grams, that in itself isn't really any indication of how precisely you know it, really, because if you've ordered 30 tons of rock and you know its mass to the nearest 0.1 grams, that's really good. It means that effectively there's almost no uncertainty in the mass that you've measured. But if you've got 0.2 grams of some drug that you're going to give a patient, but you only know that 0.2 to the nearest 0.1, that might mean that you're going to give the patient only half as much as they need, or maybe 1.5 times as much as they need. Neither one of those things could be seriously bad. So it's not really the absolute size of the uncertainty that matters, it's what that uncertainty is as a percentage of the number you're trying to measure. And so that's why we introduce this quantity of percentage uncertainty or percentage error when we're talking about numbers. And the definition is that it's the maximum error divided by the value measured times 100. So if, for example, we have a mass that's measured as 13.75 grams and we know that the maximum error is 0.005 grams, that would mean that the percentage uncertainty is just equal to 0.005 divided by 13.75 times 100, which is 0.036%. Okay, so that's a very small percentage error. So that means that if your maximum error is as small as that, then a mass of that reading of that sort of size you can measure really very accurately. Now, most of the time in chemistry questions, they will just tell you what the percentage error is. So, for example, you might have a pipette, which is notionally 25.0 cm cubed, but they might tell you that the maximum error is, say, 0.02 cm cubed. And then again, it would be easy to work out that the percentage error is 0.02 over 25.0 times 100, which is 0.08%. So again, fairly small percentage error, because a pipette's a pretty accurately calibrated bit of equipment, so you get a decent percentage error like that. It's just possible they would ask you to decide what you think the percentage error is based on the calibrations on a piece of equipment. So, for example, if we think about, let's go back to our 13.75 grams on the balance again, and think about that. So the balance reads to 2 decimal places, so that would mean that the possible readings in that region would be 13.74, 13.75 or 13.76. And of course the real mass could be anywhere in between there and there, or in between there and there, but we can see that there's a sort of dividing line. So if the real mass was 13.745, anything there or above would round up to 13.75. but anything that was smaller than that would round down to 13.74. So really, if the balance is reading 13.75, it could actually be reading anything the true mass could be anything down to 13.745, because that would round up to 13.75. But equally, of course, it could be bigger than 13.75, so long as it's not bigger than 13.755, it would round down to 13.75. Anything bigger than that would round upwards. So you can see that in either direction, that's where the idea of the maximum error being 0.005 grams would come from. Now that ignores any limitations in the actual quality of the equipment, any uncertainty that comes from the fact that what reads that may not be exactly that, and that of course you can't know just by looking at the numbers. But it is worth thinking about the fact that there is this fundamental limitation when you have a digital piece of equipment, that last digit places a fundamental limitation on what the percentage uncertainty could be. Okay, so there are a couple of issues related to percentage uncertainty which you're likely to get asked about. One of them is what you can do to improve it, to get a smaller percentage uncertainty in your number. And you can see from the definition that if you want to make this answer smaller, you've got two possibilities. You either make the top line smaller, or you make the bottom line bigger, and either one of those will make the answer smaller. So if we decrease that or increase that, then either of those will give you a decreased percentage uncertainty. So what you have to think about is what can you do to improve either of those things. So to decrease the maximum error is normally going to mean that you need a better bit of equipment. So for example, if we're talking about a balance, if you have a balance that reads to 3 decimal places instead of 2, that's clearly going to decrease the maximum error. So you can make suggestions like that, but don't just say need a better balance, because they're going to want to know better in what sense. So specify something like a balance that reads to 3 decimal places instead of 2 decimal places, and then that would be a valid way of saying, yeah, that would decrease the uncertainty in percentage terms. What about the bottom line then, the value measured? Well, you can see that if you measure a bigger value, the percentage uncertainty is going to be smaller. So if instead of using 13.75 grams, we use twice as much, bottom line is going to be twice as big, and that means the percentage uncertainty will only be half as big. So that's an important idea, that by scaling up to a larger value measured, then the percentage uncertainty can be decreased. And that often is going to be a more realistic thing to do than buying a new balance or whatever it might be. So always think about, can you easily increase the size of the value measured, and with a mass that would be a reasonable thing to propose to do. And the second issue we need to be clear about is that some of the kinds of measurements that you routinely use in calculations depend actually on making 2 measurements with your equipment. So an example is using a burette like this. If you did this experiment where you had your burette was initially filled up so the volume reading was 0.45, and then you do your experiment, you reach the end point where you've neutralized or whatever it is you're doing, and you say, oh yeah, the final volume is 24.00, then you know that the titer is 24.00 minus 0.45, which is 23.55 cm cubed. But the complication is, if we're thinking about percentage uncertainty, that in order to get this number, you had to read the burette twice. First at the beginning and then again at the end, and each one of those readings will have an uncertainty associated with it. So if we think about how a burette works, each time you make a reading there's an uncertainty. So this initial one we've listed as 0.45 cm cubed, so that would mean that this Remember, the burette has gradations every 0.1, so 0.45 would mean that we thought that the volume was closest to being halfway in between 0.4 and 0.5. So we might think, oh yeah, that means that, the meniscus looks like this. But of course, all we're really saying is that it's closer to 0.45 than it is to 0.40. So it might actually have been, that. Or that. And we would still have listed it as 0.45. And just like we said with the with the balance, we can sort of put a limit on what the percentage uncertainty would be based on that, because you can see anything bigger than 0.425 would round up to 0.45, or anything less than 0.475 would round down. So the maximum error is equal to 0.025 cm cubed in either direction on that reading. However, when we read the burette again to get the final volume, then independently, again, you're going to have that same maximum error for the same reason. And you can see that that gives you a bigger overall possible maximum error than you would get from just one. Because, for example, your initial volume reading could actually have been slightly lower than the value you put in, and your final one, which is going there, that could have been slightly bigger going that way. So the true volume might actually be bigger not just by 0.025 but by 0.025 that way and 0.025 that way, so it could be off by 0.05. So what does that mean? Well, all it means is that when the value you're using depends on two measurements, you have to add up the maximum error on each individual measurement. So there we have it then. We've got the maximum error is 0.025 cm cubed per measurement, but the titer depends on two measurement readings, the initial one and the final one. And that means that the maximum error on the titer is 2 times 0.025, which is 0.050 cm cubed. So the percentage error on the titer is that maximum error 0.05 divided by 23.55 times 100, which equals 0.21% would be the error on that reading. Now, say in a question, quite often they won't, or in fact usually they won't expect you to deduce what the percentage uncertainty is like that, because in a way that's liable to be underestimating it, because that's based only on the sort of resolution of the equipment. But there will also be some percentage uncertainty that comes from, inaccuracies in the calibration, from the fact that the glass changes size slightly as the temperature changes, all kinds of things like that. So you're liable to be underestimating the percentage uncertainty if you just work it out from the resolution like that. So quite commonly they'll just tell you what the percentage uncertainty on each reading is, but you then have to remember about combining the errors like that. So other situations where you have to add up errors like that, there are a couple of common ones that you come across. One is on delta T, temperature changes. When you're doing, for example, MC delta T experiment, that you'll have your initial temperature and your final temperature, and they will each have an individual maximum error, which you then have to add up to get the total maximum error on the temperature. Another one is mass, where you have, for example, a situation where you have your pot plus compound, which you weigh, and then you empty the compound into the reaction flask or whatever, and then you just weigh the empty pot. And that's the standard way to get the mass of the compound that you used. So you get mass of the compound is equal to the pot plus compound minus the pot. So you're making two measurements again, and each one of them will have its own maximum error based on the calibration of the balance that you're using, and you have to add up those maximum errors to get the total maximum error in that kind of experiment.